A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians. Welcome back to one of the last videos here on this channel. Yes, the channel is gonna be done after 2 more mathematics videos, including this one. So yeah, make sure to watch the video to the end, to pay tributes to this channel, to spend a bit more time with your papa and the family in those last moments. There's also going to be a final video explaining everything. So yeah, I hope you're going to enjoy today's video, which has been once again sponsored by the wonderful people over on Brilliant. They have done so much for me and the channel over the years, so definitely make sure to watch till the end to pay tributes to this channel and to spend some more time with your papa and the family, and also to check out Brilliant. They have done God's work for me and an entire community. So yeah, please check them out. Also, I have very sore throat and I caught a cold. Everything is coming my way at the same time. So if you see any cuts, I'm just clearing my throat. And yeah, now we are going to dive right in. Today's video I found over on Boomer Book, or today's video topic, which was this one right here. And it's a very clear statement. You just have to think about it for like 10 seconds and then you basically know the answer. But we want to turn this into something more mathematically accurate or mathematically worthwhile while we are at it. So try it out and post your solution down below. And once you're done, keep watching the video. So what do we have? We have a function which, if we put a certain value of another function into function composition, we are going to get x out on the other side. And as always, what you want to do is you want to find x. And the cool thing is, if we were to find a certain value for x such that the argument of our composition right here is satisfied, we are also done with the problem because it just spits out x overall. And there are basically 2 cases that you can go about. So either your x squared is equal to 1/2, or if you use the commutativity in real numbers, we have that the natural log of x is equal to 1/2. We only have those 2 cases. So let us try it out. So if x squared is so this is case 1. If x squared is equal to 1/2, that just means that x is equal to plus or minus 1 over the square root of 2. If we were to plug this into our natural log, then we are going to get out the natural log of, so we can just take the positive branch, the negative branch really doesn't work out for the natural log, 1 over square root of 2. This must be equal to e, but obviously this is not the case. This is something like 1/2 ln of 1/2, or negative 1/2 times the ln. So this really doesn't work out because this would pose a negative value and e is strictly positive. So the only thing that is really working out other than that is case 2, such that the natural log of x is equal to 1/2. If this right here is the case, what we are just going to do is we are going to use base e on both sides to solve for x. So we are going to end up with x being equal to e to the 1/2 power, or in other words, the positive square root of e. Now we just need to check if we get e out if we plug it into x squared. And obviously, if we take square root of e squared, this is going to result in e. So our solution to this problem is equal to the square root of e. Okay, that is cool. And this is very easy to see. But as mentioned previously, we want to make this a bit worthwhile. And for this, I found out something very peculiar, or it's just a basic thing that has to do with functions. And I also covered it a tiny little bit when we talked about automorphisms a while back here on this channel. Now, what happens if we do function composition and we get just x out? This just means that we plug the inverse function of our function in and got the identity out. By definition, this is how inverse functions work. If we take composition of functions f and we take it into composition with its inverse function, we always get out the identity function, which is x. Group theoretically speaking. Now this really turns everything around quite a bit, and this can lead to a very interesting result, to say at least. Now the cool thing is, if we just suppose that this right here is the inverse function, what we can also do is we can apply the inverse function on both sides here, and we are going to end up with the inverse function of x is equal to, and if we apply the inverse function to the function, we are going to end up with x squared plus natural log of x. Now, why is this interesting? Well, this is in the sense interesting that we can now solve for x, because this is what we wanted to do. We wanted to find a value x such that this right here is overall satisfied. So why not do this? Let's go. We are going to set this equal to y, just to make matters a bit easier, notation-wise. And now we are going to try to solve for x. And this can be a tiny little bit tricky, but we can work around this with very special function. And if you got a sharp eye, you might already see where this is going. So the first thing we are going to do is we are going to bring everything into natural log form, especially this left-hand side, because then we can use the same property that we did here, raising both sides to base e, and then we can basically simplify. And the cool thing about logarithms is that with logarithms, you can use addition to turn it into multiplication. Now, let's go ahead and get started. What we can do is we can turn x squared into the natural log of e to the x squared. So this right here is the same as saying we have the natural log of e to the x squared plus the natural log of x is equal to y. Now, by the logarithm properties, addition turns into multiplication of the arguments. So this right here is the same as saying we have the natural log of e to the x squared times x is equal to y. And now here's where the fun is going to begin. We want to solve for x. So we are going to take base e, once again, just like we did here, leaving us overall with e to the x squared. I'm going to put the x to the front, is equal to the e to the y. But now you might ask yourself, hey, Papa Flammy, how are you going to solve for x here? And this is something we have covered here on this channel quite a lot. It has been covered over the years on YouTube quite a lot in general. We are going to make use of the Lambert W function. This is where the beautiful stuff comes in, leading to a very cool result at the very end. Now, just if you're not familiar with the Lambert W function, if we got a function z times e to the z is equal to f of z, then the Lambert W function is defined as the inverse function. It also depends on the branch, which solves this function right here for the argument z. So if we were to apply the inverse function Lambert W to what we have right here, z times e to the z, this is what is going to spit out z overall. Now this is how the Lambert W function works. So what we need to do is, overall, we need to basically bring this into a form set with the set also up here in the exponent, such that we can solve for this set. So I'm going to put everything here once again. So we got x times e to the x squared is equal to e to the y. Now, there are basically two ways to get ourselves the same thing down here as up here, and only one is really going to work out. So the first thing you might think of probably is, how about we basically get rid of the square that we have up here. This is something that you could do, for example. But the thing is, if we were to get rid of the squared up here, you would need to take kind of a square root, but this also doesn't work out because this right here is the exponentiation of the exponentiation. It's not that easy. There's no function equation for the exponential function which is going to satisfy this. But what we can do is, instead of taking a square root in some kind of way, we could just square both sides. And this is going to make matters easier. So let us square both sides that we got right here. And by exponentiation rules, what are we going to get? We are going to get overall. So by exponentiating, we are going to make use of the rule that we are going to exponentiate each and every individual part. So we are going to get x squared, which is good. And then we are going to get e to the x squared, but squared. E to the x squared squared is the same as e to the 2x squared. And this is nice. This works out. So this right here is the same as x squared times e to the 2x squared is equal to, and by the same arguments, we get e to the 2y. Okay. Now we are pretty darn close to what we want to have. The only thing that's missing is a 2 right here. And this is rather easy to do by just multiplying both sides by a 2, basically. So if we were to multiply both sides by 2, I'm going to just take this out of the equation right here. We are going to end up with 2x squared times e to the 2x squared, which is what we want. This right here is our z, is equal to 2 times e to the 2y. And now we can make use of the Lambert W function on both sides to get ourselves. If we apply the Lambert W function on the side, what we are going to get out is just the Lambert W function of no, it's just z. I'm terribly sorry. So 2 times x squared. This is how the Lambert W function is defined. So we are just going to end up with our value of z, just like we have here. So we're going to end up with 2x squared is equal to Lambert W of 2e to the 2y. Okay, perfect. And now we can just simply solve for our value x by dividing both sides by 2 and then taking the square root. We are going to end up with x being equal to, and it really depends on the branch, but we are going to take plus and minus roots. So we are going to end up with plus or minus 1 over the square root of 2 times the Lambert W function of the square root of the Lambert W function of 2 times e to the 2y. This right here is our value for x. And how does this help exactly? Well, it does help in the sense that our original y is the argument that we wanted to plug in, 1/2 plus e. This is exactly what we did. Remember, if we had f to negative 1 of x, this is the same if we were to apply f once again, like this. Meaning our value y is nothing other than x squared plus ln x. This is what we got right here. And we want to plug this exact value in. So, by plugging this in, we are going to end up with x is equal to plus or minus 1 over the square root of 2 times the square root of the Lambert W function of 2 times e to the 2. And then we are going to get 1/2 plus e. So the 1/2 part is just going to turn into 1 and then plus 2e. Now you can simplify this a bit more by using exponentiation rules basically and turn this into 2 times e to the 2e. This is something that you can do. But the very cool thing about this is that we know from our initial statement that this is also equal to the square root of e. And this is the cool result that I was talking about. Just because it's very hard to find solutions to the Lambert W function non-analytically, like getting yourselves values for the Lambert W function by just basically plugging stuff in. It's really hard to do because this is, for example, defined on the main branch by a Taylor series expansion. And in a normal case, you can just get values numerically in some kind of way. But here, what we did, we basically reformed everything and got ourselves a value for the Lambert W function of this very argument that we have right here. And you can play around with this idea a tiny little bit more. By basically solving this a tiny little bit more, we can square both sides and multiply both sides by 2, giving us overall that the Lambert W function of 2 times e to the 1 plus 2e is hence equal to 2 times e. This is what you basically can gather from what we have here. And this is very cool that you can plug a value of e into the eve power in some kind of way and get yourself an irrational number and transcendental number out on the other side. Yeah, this right here is a bit more of an expanded solution to the problem from the very start. And I hope you did enjoy what you have seen today. And if you want to see more mathematics or maybe even physics, computer sciences or chemistry, everything in the STEM field, then the contents of today's sponsor Brilliant might be the perfect fit for you. If you had no idea what we did today when it came to the so-called product log, the Lambert W function, then this is not a problem at all. In mathematics and physics, there are so many special functions flying around that it's easy to lose an overview of all of those. But Preint might be of help to you when it comes to those special functions and all those analytical things in general. Preint is your source for some of the best online learning content that you can find out there on the World Wide Web. Really doesn't matter if you want to learn something about the mathematics that we did today, physics, computer science, chemistry. They got something up their sleeve for all of you out there, and it really doesn't matter if you're university level right now or high school level. It really does not matter. You tell Preint where you are in your studies right now, and they give you exactly the courses that are the perfect fit for you at the moment, such that you can start off very slow but get smarter and more sophisticated in no time at all. I mean it. Preint is extremely good at transferring knowledge over to their users, and the best thing about Preint is their visual learning concept, where they use all those cool graphics and visualizations that you can play around with to get better at the topics at hand. It's seriously magical what they offer to the STEM community, and you should just check it out for yourself. Don't just look at all those graphics and visualizations that I have shown you on the screen here at the moment. Just check it out for yourself by using my link here at the top of the description, preint.org/flambymaths, or my QR code somewhere up here in the corner. With it, you're going to get a 30-day free trial of amazing awesomeness. Try out the whole landscape of Preint for completely free and see if it's something for you. And if you feel like this could turn into a long-term relationship between you and the services, then it's definitely time to use the link here in its entirety and get 20% off an annual premium subscription. It's seriously worth it, and they add so much new content on a regular basis. I seriously love what they provide and what they have provided over the years to my community and many other communities all over the internet and YouTube. And it's really, really good what they did. It's just hard to put into words how much I appreciate what they do. So definitely make sure to check it out and support the channel this way. And I hope you did enjoy today's video. I'm very sorry for having caught a cold, but I hope I'm feeling better in the next video, in the final math video. And up until the next video, I wish you guys a fabulous day. See ya.